Hello everyone. We will start week 6, and in this week, we will solve some uniformly distributed beam problem, verifying distributed beam problem, and also we will solve class problem related to the frame beam problem. Okay, so let's start. So the first problem which I selected is related to the beam problem, and it is saying that there is a span where there are two kind of distributed load. In the figure 1 it is a uniformly distributed load, and in figure 2 it is also uniformly distributed load, but in this figure it is simply supported, but in this figure you can see that it is fixed supported, and it is asking to find the displacement and slope of each node, and it is given that the length of each beam is 3 meter, Young's modulus is 200 gigapascal, and W is 20,000 Newton per meter, and moment of inertia is 30 × 10⁻⁻6 meter raised to the power 4. Okay, so before going to this problem, we will try to understand the variational form of the beam equation, where sir has already taught us. So let's first start from that, and then we will try to formulate how to solve these two beam problem. So we already saw that this is the governing equation which required to reach the variational form of the beam equation. Okay, so this is the governing equation. Okay, so when I write W and we will try to find the moment, then we get the governing equation is like this. Equal to 0, and this is the sign convention which we are using throughout this course. Like if it is a downward, then we will take it as a positive moment. If it is a clockwise, then we will take it as a positive load, displacement. If it is a downward, then we will take it as a positive, and slope, if it is a downward clockwise, then we will take it as a positive. So this is the governing equation. We will try to convert it into the variational form. So the variational form in the global form is something like this. And if I apply integration by part, then we arrive the above equation like this. And also we have some natural boundary condition and essential boundary condition. So I will write these as a separate this is a natural boundary condition, and this is essential boundary condition. Okay, so for each node, if I see for the beam problem, suppose this is the arbitrary element. So this is the displacement. Suppose it is a node 1 and it is a node 2, and the displacement at node 1 we will write W1, and the slope we will write W1 dash, and this is W2 and this is W2 dash. So for each element, these are variables which we will use. Okay, and we already saw that we are taking W in terms of zeta is something like this. And what are shape function? This n1, n2, n3, n4, we are using Hermite polynomial shape function. So these are n1, this is n1, this is n2, this is n3, and this is n4. Okay, and for the coordinate x, we are using the Lagrange shape function. And this is, since this is for element E, so we will write E. Okay. Now we will move for the elemental stiffness matrix, how we will write it. So if we differentiate this, and this can also be written as something like this: 1 minus zeta by 2, 1 plus zeta by 2, and this one is x1e and this one is x2e. Okay, so if we find dxe, then we already saw that if I differentiate dxc by d zeta, then we already saw that this becomes 1 by 2 minus 1 by 2 and 1 by 2, and this is x1e and this is x2e, and this is nothing but LE by 2. So I can write dxe as this term. This term is nothing but the Jacobian for this elemental, so I will write it as j d zeta. Okay, so why we are doing this? Because I want to convert the elemental. If I want to convert this integration for the each element in our elemental form, so that's why we are trying to, thus we are trying to substitute the variable, change the variable, not substitute, change the, I want to change the variable. Okay, so now so we already saw that if we differentiate this equation, because we already saw that we need the second order derivative of this w. Okay, so if we differentiate this first times, so del w by del x, so what it will be? It will be del w by del zeta into del zeta by del x. Okay, and here we can see that the whole w is in terms of zeta, because n1, n2, n3 and n4 are in is the function of zeta. Okay, so this will become n dash into, and del zeta by del x, we already saw that it is nothing but 1 by j, and I can also write it as what, and here n dash times, because it is also is the w nodal coordinate. Okay, so we will write it as a w e hat. Okay, into del zeta by del x, and that is nothing but j, so I can write 2 by l e. Okay, since it is a first derivative, now we have to write the second derivative. Okay, so the second derivative is nothing but n double dash zeta, and it will be w e, and it will be 2 by l e. Okay, since 2 by l e, again I have to write del w by del x. I will explain it again. Okay, then you will understand. So what is that? Del w by del x, so I have to write del w by del zeta del w by del x into del zeta by del x. Okay, so it will become n double dash zeta and w e, and it will become, again we will multiply with 2 by l e, so it will become 4 by l e raised to the power 2. Okay, so this is the thing, and the same thing we will do it for this. Okay, so it will become n double dash zeta, and it will be w, in terms of this I will write it as a v. Okay, into 4 by l e square. Okay, now we will substitute all these in this equation. Okay, after substituting, we saw that it becomes something like this. EI minus 1 to 1, and this is B. For this moment this becomes B. Okay, so this will be B transpose B, and J, the whole term, actually the whole term, this will be N double dash zeta into 4 by LE square, okay, into VE hat. This whole term will become B. Okay, so that's why it will become B transpose B, and since we are changing the variable from dx to del zeta, so again J will come. Okay, so J del zeta, okay, equal to since we have to also convert it as a from the right hand side, so we will write it as a minus 1 to 1, and since there is no such derivative, we have to notice it as a there is no such derivative, so we will directly write as that is a N transpose Q, and since we are changing the variable, so Jacobian will come into the picture, and del zeta. And we are neglecting the boundary condition for this moment, because we already know that later we can change the boundary condition in the global force matrix. So this is the governing equation for each element, we have to use it. Okay, now the thing is Q can be a uniformly distributed load, it can be a varying distributed load, so Q can be a constant also, and Q can be a function of X also, so we need to change accordingly. Okay, now let's move and we will try to implement it in the MATLAB. Okay, so this is the problem number 1. Okay, so we already saw that we are solving the problem. So now what we will do is we will mesh and we will create a node. Okay, so this is the beam, and suppose this is the node number 1, this is the node number 2, this is the node number 3, this is the node number 4, and this is the node number 5. Since the whole span, the length of whole span is L, so that's why, so this will become L by 4, and this will become 2L by so L by 4, L by 2. L by 2, and again we have to add L by 2, so it will become 3L by 4, and this will be, again I am writing the coordinates, okay, and this will be L. Okay, I am not showing that this is the length, okay, I am just saying that this is the nodal coordinates. Okay, so so for node 1, if I write, so I can write as a W1 dash, W2 and W2 dash. So this is the meshing I am using it. So I have used 4 nodes. Okay, so this is the element number 1, this is the element number 2, this is the element number 3, and this is the element number 4. Okay, so we are using 4 elements. So I can also see that I want to see what is the maximum deflection. We already know that the analytical solution of the simply supported beam problem is like this. W max, we already know that what is this, 5 Q L raised to the power 4 divided by 384 and EI. Okay, and this is happening at point 3. It is happening at node 3. And what is the maximum slope? The maximum slope formula I have written, it is QLQ. QL raised to the power 3 and 24 EI. 24 EI. 24 EI. And we will verify the FEA solution by this. And where it is the maximum displacement, maximum slope, we already know that the maximum slope is this at node this, and the beam will deflect something like this. Here this one is the maximum, okay, theta max, and this one is the theta max. Since we already know that this, since it is a anti-clockwise, so this theta should come negative, and this is a clockwise, so that's why this theta should come positive. Okay, and here it is a maximum displacement. This is the W max. Okay, now we will move to the MATLAB code and we will try to understand this. Okay, so yeah, so this is the coordinates. So you can see that for node for element 1, this is the coordinate 0, L by 4, L by 2, 3L by 4 and L, and this is the element connectivity. What is the element connectivity? For element 1 it is node 1 2, for element 2 it is 2 3, and for element 3 3 4, and the last element is 4 5. Okay, so this is the number of elements it will get, and this is the degree of freedom. We already know that for each node we have to take 2 degree of freedom. One is vertical displacement, which is nothing but the deflection, and second one is the slope. Okay, and this is the K global, which I have initialized, all elements are 0, F global, and this is the Q naught. Okay, so Q naught is nothing but the UDL, okay, load, that is 20,000. So here I have written as a Q. Okay, and all elements have the same modulus of elasticity and have the same moment of inertia. Okay, so this is the code. So you can see that first it will take the node, local coordinate, moment of inertia, modulus of elasticity, and then it will calculate the localized or elemental stiffness matrix. Okay, so we will see how it is calculating. So first I will try to clear all the variables. Okay, first it will move to the stiffness matrix. So we will see how this function looks like. So first it will take the nodal coordinate and modulus of elasticity and moment of inertia. Since I have initialized xi, so that is the variable where it is varying from -1 to 1, and this is the length of that element. It will take the second coordinate, I mean the x2 and x1, and this is the nmat. This is nothing but the shape function matrix. So you can see that this is the shape function matrix, and it is Hermite cubic polynomial. So that's why these are n1, n2, n3 and n4, which I have already shown. Okay, and this is the B, and we already saw that what is the B. B is nothing but, where it is B, yeah, so B is this, n double dash, and I means double derivative of n into 4le square. Okay, so that's why it is 4 divided by le square, and it will differentiate n mat 2 times. Okay, because we need the second derivative, so that's why. And we already saw that when you differentiate it, so this factor will come into the picture. Okay, this factor will come into the picture, so that's why I have written b here. Okay, and this is the k local, so we already know that it should be 4 by 4 matrix, and I am using the 4 number of points for each element. Since it is a cubic polynomial, cubic Hermite polynomial, I am using it, so it will provide xi points and weights. Okay, and after getting xi and weight, it will first substitute at b. And what is b? This is b. Okay, and the integrand, we already know that this is the integrand. What it is? ei b transpose b and j. Okay, and j is nothing but le by 2 and b transpose b. Okay, and after running each loop, it will added in the zero matrix. Okay, by using the Gauss Gauss quadrature integral. Okay, and we will see how this matrix will look like if we run the code. Suppose I want to see so first initialize, because it is in the symbolic form, so first I have to initialize sims, that is ei. Okay, and le. Okay, let's see le. Okay, so this is the it has initialized. Now I will give this nodal coordinate. Suppose I want to see the first element. Okay, that is the coordinate, suppose 0 and le. Okay, so I have initialized it, and e and I have already given. Let's see what this function gives. What happened? Sorry, I didn't know how to do it. Okay, so let's start. So yeah, let's run this code and we will see what it is giving. So yeah, so this thing you can see that, and this is the same matrix we already saw that, which sir has already discussed it. Okay, so this is the stiffness matrix, and you can see that it is a function of EILEQ. Okay, yeah, now we will see where the uh, force function, compute force function. Okay, so here it is a force function. So yeah, we already saw that what is the force function. Force function is nothing but n transpose q into j. Okay, there is no such derivative in it, so that's why nmat, and this is the n. Okay, and first we will initialize it, so it will be a vector of 4 by 1, and again it will integrate. Okay, so this is the GI q transpose, sorry, n transpose q times Jacobian, and Jacobian is nothing but LE by 2. Okay, let's see what is the force function it is giving, and I will also use Sims q naught. Okay, q naught. Okay, let's see what results it is giving. Okay, yeah, so you can see that. Okay, it is nothing but this 0.08833 is nothing but 1 by 12. So it is the same as we already saw that what will be the force matrix for each element. Okay, so yeah, now let's move to the problem. Okay, so first it will calculate for each element, it will take local coordinates, elasticity, moment of inertia, then it will calculate the stiffness matrix, then it will go to the force matrix, which we already saw that, and this is the indices for each element. Okay, so which means that we already saw that we need to for node 1 it should be 2j minus 1 2j, and for node 2 it should be 2j minus 1 and 2j. So it will populate the global stiffness matrix according to these indices. Okay, and similarly for the F global. Okay, and after running this code we will display K global, F global, and yeah, now we need to fix the node, because we already know that we need to find the K reduce, F reduce, and then we will get U reduce by K transpose F. Okay, and then at the place of free node we will substitute Q reduce, and then we will find the F reaction, and we will print the nodal displacement and reaction forces. Okay, let's run this code up to this point and we will see what we are getting it. So yeah, it is running. So yeah, so this is the for node 1, and this is the local coordinate, because L is 3, so that's why 0.75. This is the modulus of elasticity. This is the K local for element 1, F local, and for element 2 this is the local coordinates, and these are all K locals. Okay, and this is the stiffness matrix, this is the global force matrix, this is the reduced matrix, and this is the nodal displacement and reaction forces. Okay, now we will try to verify whether our solution is correct or not. Okay, so what we got it, we got that for element 1, let's see, here I will copy it and I will paste it. Okay, so this is the node 1, this is node 2, this is node 3, this is node 4, and this is node 5. Okay, so we saw that for node 1 there is no such displacement. Yeah, it should be. Okay, and there is a slope. Okay, and you can see that the maximum slope, whatever we are getting it, either this or this. So it's clear that, and you can see that for theta max it should be positive number, so that's why we are getting positive. And for node 5 we are getting the same deflection because symmetricity of the beam, we are getting the same displacement, same slope, but in the negative direction. Okay, now we will try to focus at node 3. Okay, so at node 3 you can see that there is no such theta. Okay, there is no slope because it becomes horizontal. I mean, if you draw a tangent line, the slope will be 0, so that's why we are getting 0 slope. Now we will try to focus this. Okay, you can also see that this is the maximum displacement which we are getting it. Okay, that is nothing but the W max. Okay, let's try to substitute with our analytical solution. So we already saw that the length of the whole beam is 3 meter, Q is 20,000, and this is the modulus of elasticity, moment of inertia. Okay, and when we are trying to find the value, that is nothing but the 5W L raised to the power 4 divided by 384 EI, we are getting 0.0035163. So you can see that it is approximately same. So since we have to see, because the MATLAB it is giving only up to the 4 decimal point, so that's why, I mean, approximately it is correct. And this is the slope, so you can see that it is also matching. Okay, so which means that our solution is correct. Okay, now we will see, we'll try to post process the solution. Okay, so for the post processing, what I am doing is I have initialized xi value, so we already know that it should vary from -1 to 1, and I am taking 50 numbers, 50 such numbers between -1 to 1, and I have initialized displacement plot, slope plot, moment plot, and shear plot, and x plot. Okay, so these are all same things which we already done it, and this is the degree of freedom. Okay, and here you can see that first it will take shape function matrix, then n, then dn, and then double. Since there is no requirement of this thing is nothing but to draw the SFD and BMD. Okay, so that's why there is no such requirement to do it. So I have also written the code for that, but I have commented it, but you can do it. Okay, so that's why I have not using, I mean, there is no such use of these two. Okay, so let me comment this thing. Okay, so yeah, and this is the Ni. What is Ni? Ni is nothing but the n value, but at different xi values. Okay, there are 50 xi values because the loop is running for 50 such xi values. Then it will find the displacement. Okay, and what is the displacement? n into u. Okay, and then we already know that we are using the x for the Lagrange shape function, so that's why I have written this, and this is the displacement plot, slope plot. It will run it. Okay, so let's plot this thing up to this point. Yeah, continue. I will continue it. So yeah, so here you can see that the displacement is maximum at this point. Okay, and 0 0 displacement at endpoints. Okay, and yeah, and we can also see that the nodal coordinate, these are nodal coordinates for the displacement. We are getting it, and you can see that this is also matching with the continuous, I mean interpolated values, and this is the slope. But but here you will be confused, because you might seen that you keep such that you might be seeing that it should be same value at endpoints, but we already saw that this value should not be same, because there is a difference of sign. One is positive and second is negative, so here it is a 0. Okay, so when you draw a line here, then with respect to this line, this graph is symmetric but with the negative sign. So we can also see that at midpoint there is no slope, so that's why slope value is 0 at this point. Okay, so this is all about the solution for one UDL problem. Okay, so let's solve this problem. And we will take one 5-minute break, and we will try to discuss this problem. Okay, so let's start the second problem. So yeah, the second problem is like this. It is saying it is fixed supported. So we will use the same code, but we will do some small modification. Okay, so again length is 3 meter and modulus of elasticity is 200 e raised to the power 9 and moment of inertia is 30 e raised to the power 6 and q is again 20,000 and the meshing will remain same. That will be we will use 4 nodes, not 4 nodes, 5 nodes. Okay, so 1 2 3 4 5. Okay, again we will do the same nodal points and these are the element connectivity. It will remain same. That will be 1 2 2 3 3 4 4 5. Okay, and q will remain same. Everything will remain same except the fixed nodes. Okay, so in this problem, the only difference is what are the degree of freedom for each node which we have fixed it. Okay, so this is the fixed beam and this is the UDL which it is acting. This is the node 1, node 2, node 3, node 4 and node 5. Okay, so for node 1 we already see that if I write, that is W1 and W dash, so these are zeros. Okay, these are fixed nodes. Okay, so which means that the coordinate the variables are 1 2. Here the variables are 3 4 5 6 7 8 and 9 10. Okay, so earlier in the previous case we fixed only 1 and 9. Okay, so we already saw that in the earlier case we only fixed 1 and 9. So where it is, yeah, 1 and 9. But in this case not only 1 but also 2 will be fixed. Okay, 2 will also be fixed, and at node 5 not only 9 but 10 will also be fixed. Okay, and everything is same, q e I, everything will remain same. Okay, now let's run this code and let's see what result we are getting it. So yeah, so here you can see that it is showing each and every stiffness matrix, elemental force matrix. We will see later this thing. Okay, and these are results, and yeah, this is the result for the nodal displacement. Okay, this is the result for the nodal displacement, and we will write it. So there is another 0 which we have mixed it. First I will paste it again. So yeah, this is the result which we are getting it. So we can see that this is the nodal displacement for node 1, this is for node 2, this is for node 3, this is for node 4, and this is for node 5. So at node 3 we are expecting that the vertical displacement should be maximum. Okay, so that's why we are getting it as a maximum displacement. Okay, and there should be no slope, so that's why there is no slope. Here also there is no slope, here also there is no slope, so that's why these values at end points are 0, and not also that, but also the vertical displacements are also 0. And we can also expect that the node point 2 and node point 4 are symmetric. Okay, so you can also see that these two numbers are same. Okay, which means the vertical displacements are same, but the only difference is slope. Magnitude wise slope is also same, but only the difference is their sign, the rotation. Okay, so yeah, so you can see that this is the maximum displacement and this is the maximum slope which we are getting it. Okay, now let's try to verify the analytical solution. Okay, so we already know that theta max formula and W max formula, and what is that? We need to check it on the internet. Actually I forgot that. So yeah, so this is the formula for the maximum displacement, that is W in our case it is Q. So Q L raised to the power 4 divided by 384, and what is the slope? That is Wx square divided by 24 EI L minus x raised to the power 2. Since it is not at the midpoint, so that's why it is showing in terms of x. So let's solve. Let's try to find theta max. Okay, So we already, by intuition, we already know that theta max will be where, at point 2. Okay, so if we replace it, x equal to, what is that, L by 4. So what it should be, W L by 4 raised to the power 2, 24 EI into L by 4, that will be 3L by 4 raised to the power 2. So W L raised to the power 4 into 9 divided by 64 into 24 EI. Okay, yeah, it should be correct only. So W L by 4, 3L by 4, 24 EI. So yeah. Okay, so let's check it. Let's go to the Mathematica and we will try to find the values. Okay, so in our case, what is the W? W is 5 divided by 384. First let's see. Yeah, 0.7031. Okay, so you can see that it is exactly matching. Now let's see what is the slope. So that is 9 times QL raised to the power, okay, it should be x only. I think it's not correct. The slope should be of power 3 only. Okay, leave it. You can find on the internet, and hopefully it should be correct. Let's erase this. Okay, so yeah, so this is the solution for two types of beam. Okay, now let's move to another type of beam where UVL is connected. Okay, so up to this point, yeah, let's solve one UVL problem. And I think sir has already discussed in the one problem in the class. Okay, so let's do that. This is the problem number 3. Okay, and what is that? The problem is something like this. Okay, it is UVL, not UVL, VDL, varying distributed load, and it is a Q naught, and this is the length 0, x, and the span again L and everything are same, L, W, I mean in this case it is Q naught, Q naught, E and I, everything are same, but only the difference is should not be fixed here. Yeah, fixed should be here. Okay, the difference is the force is also acting here, F naught and moment. Okay, and so yeah, what are those values? Those values are, I will write each and every values here. And L is 3 meter, Q naught is 20,000 Newton per meter, and modulus of elasticity is 20 gigapascal. Moment of inertia is 30 into 10 to the power minus 6 meter raised to the power 4. F naught it is given as 50,000 Newton, and M naught here it is given 15,000. Okay, 15,000 Newton meter. Okay, so let's solve this problem and we will see the result. Okay, so I think I have made some mistake here, so that's why I'm getting that not a value, not a number. So so here you can see that I have made one mistake. So this is the mistake, so that's why, because if I take the value 200 E9, then there will be a mismatch because of the power 10 raised to the power. So that's why it is coming out this kind of error. So yeah, we need to take care of all this while running the code. So now we will see the result. So yeah, so here you can see that the deflection will be 0, so which is as expected because it is a fixed point. So that's why deflection should be 0 at this point. And so yeah, so notes are also correct, 1 2. Yeah, and this is the displacement, so you can see that the maximum displacement will be at node 5, and also as expected the slope will be also at node 5. Okay, and you can see that this beam will bend like this. Okay, so that's why it is coming out positive. Okay, so this is all about the beam problem. Now you can solve every kind of problem related to this. Okay, so let's start the next problem, that is the frame related. And this problem I picked it from one book, and sir has already discussed about one frame problem. And let's see. So this problem I will not discuss. This problem we will do it later. Let's discuss the sir problem which he has done it in the class. This is the class problem 1, this is the class problem 2, and the problem was like this. If I am not wrong, so that was like this. It is a fixed point, this one is the fixed point, and there was a UDL in this frame, and one force was something like 2p and another force was something like 4p, and I need to see that, yeah, is that whether correct or not. Yeah, one was 2p and one was 4p, and the nodal coordinates was like this, and this one was L1, this one was L2, and this one was L3 if I am not wrong. So that, and this is the node 1, node 2, node 3 and node 4, and this is the element 1, element 2 and element 3 and the cube. So to solve this problem, we already saw that we are treating each frame. If we talk about this frame, then we can see that this frame is not only sorry yeah so yeah this frame is not only have the transverse load, but also it has the axial load. So it will have, if I talk about one element, Suppose there is one general element. So let's this is the node 1 of this element, and this is the node 2 of this element. So here we can see that it has the force 1, that is axial load, the moment, that is okay, yeah, so this is the force 1 axial load, this is the force 2, that is the transverse load, and also there is a moment which is acting on this node. And similarly on this node also, I will write this as E, okay, yeah, it's fine. So also it has F1 2 and F2 2, and moment is also acting on this. And if I talk about the displacement, these are all about the forces which is acting on it. If I talk about the displacement for the general element, since in general it will not be in the horizontal direction, but it can be in any direction. If I talk about, and also this is in the local, this is the local coordinate axis. These are all in the local coordinate axis, okay. And suppose this beam also has this displacement. Let's see, it is u1, u2, and also it is rotating, that is suppose theta 1, and it is node 1 and it is node 2. Similarly this node has u and 1, yeah, so this also has u1 2, u2 2, and theta 2, okay. So this kind of displacements are having with this element, okay. So which means that we need to create a stiffness matrix. We need to create a stiffness matrix for each element by beam and also by a bar. Bar means such element which has only axial load. Only axial load it is acting, okay. And if I considering beam, which means that it has only a transverse load it is acting. 1 2 and ft2 and moment are acting. So we need to create a beam stiffness matrix and a bar stiffness matrix, and then we will create elemental stiffness matrix by adding beam and bar plus bar, okay. But yeah, we need to also take care of that. If I see the elemental stiffness matrix for beam, the dimension will be different, and if we treat that element as a bar, then the dimension of ke bar will be different. But one thing we can do that if I treating this as a beam, then we already know that there will be no displacement along the axial direction, okay, but in the transverse direction and rotation will be there. So in axial direction, the displacement in the axial direction, we can put 0. Similarly, if I write the stiffness matrix for the bar element, then we already know that there will be only the axial deformation or axial displacement, and the transverse and the rotation we can keep it as a 0. Okay, so if I write the displacement, if I write the displacement for one element, then we can see that it will have u1e, u2e, u3e for one node, and similarly, and I will write it as 1 here, 1 1 1. Similarly, for node 2, I can write u1, u2, u3 and 2 2 2, and I will write e e e. Okay, so this kind of displacement matrix we have to use. And similarly for force, I will write f1, f1, f2, f3. Similarly f1, f2 and f3, and since it is a first node, so I will write 1, and this is the second node, I will write 2, and this is the element, general element, so I have to write this. And all these are, we need to take care, all these are in the local coordinate axis. Okay, and we already saw that if I want to convert the whole elemental stiffness matrix into the local, suppose this is a K, yeah, so see, if I want to write in the global coordinate axis, then I can write Q multiply KE and Q, and we already saw that the Q matrix will be something like this, LM 0 0 0, okay, and M minus L 0 0 0 0 0 1 0 0 0 0 0 0, it will be L M 0 0 0 0 M minus L 0 0 0 0 0 0 1. And since it should be Q KE Q transpose, okay, but we can see that this matrix is symmetric, so it won't matter whether you are using Q or Q transpose. Okay, in the same way, since all these are in the local coordinate axis, so if I want to write in the global coordinate axis, then I have to multiply Q times FE. Okay, so yeah, so this thing we need to do, and we already know that if I want to write KE beam, and we already have the matrix, and if I want the KE bar, we already have the matrix, and we will add them up, and all the processes will be same. So let's see how our code will run in this case. So this is the class problem 1, and this is the same problem which sir has discussed. So let's see. So here this is the nodal coordinate, so I can see that for node 1 the coordinate is 0 0, for node 2 it is 0 0.5, for node 3 it will be 0.1 0.54, node 4 it will be this. And what is the connectivity? Connectivity for element 1 is 1 2, for element 2 is 2 3, and for element 3 is 3 4. And these are area, moment of inertia, elasticity, modulus of elasticity, and yeah, and this is the degree of freedom, okay, where we are fixing all those nodes. So here I can see that this node is fixed, okay. So the degree of freedom will be lost by 1 2 3, and this is the moving, so that's why 1 2 3, and there will be 4 5 6, okay, 7 8 9, and again 10 11 12 are fixed, so that's why we are not writing here, okay. So let's see how this code will work. So first what we will do is we will find L and M and the length of the each element, and also we will accordingly we will write the transformation matrix. So this is the transformation matrix, and we can see that the uniformly distributed load is only acting on element 1. So that's why I have written if condition, if E equal to 1, then we will use Q equal to 500, else if it is not the element 1, then we will use Q equal to 0. Let's go to the compute beam stiffness matrix. So here you can see that I have used two functions. One is the compute stiffness matrix and second one is compute bar matrix. So let's see compute beam matrix, okay. So here all these are same, but there is a bit difference in the beam matrix. Since earlier when I was using the only beam problem, then you saw that the first element was not 0. So but here you can see that I am trying to write this compute beam stiffness matrix is 6 by 6, because we already know that the displacement in the x direction, if you treat it as a beam, then it will be a 0. So that's why I have written the first element as 0, and rest of the nmat will be as it is. And here also the since this is for the node 1, okay, and this is for the node 2, and for node 2 also you can see that there is no such displacement because of the beam, if you are treating it as a beam. So that's why I have written 0, and this whole function will return a matrix 6 by 6, okay. So yeah, everything else will be same, okay. And now we will move to the compute bar matrix, and we already know that in the case of bar matrix it is simple as like this. If I treat as a bar matrix, then we already saw that it will be something like A E by L E and 1 minus 1 minus 1 and 1, okay. So what here in this case also, since I have to add KE beam and KE bar, so that's why I need to create KE bar also 6 by 6 matrix, okay. So here also you can see that the displacement along x axis I have written 1, else y and theta are 0, and again displacement along x axis minus 1 and 0 0. So in this way we can create compute bar matrix, okay. So these two functions are all about the stiffness matrix, okay. So then again we will see compute force matrix. Compute force matrix will be same, and this will be because of the beam, okay. We already saw that if you treat it as a bar, then the latter we will apply the boundary condition in the global force matrix. So in the if I talk about the elemental force matrix in the case of bar, then the all element force will be 0. I mean all the entries in the force will be 0, and later we can add as a boundary condition, then it will be automatically enter into the global force matrix. But into the compute force matrix, for the case of bar, we need to create a actually we need to integrate, because we already saw that that is nothing but the q into n transpose. We already saw that that was n transpose q into j. So that's why it requires a integration. Okay, so that's why we need to create a function for that. So here you can see that I have to write q, that is this is the Jacobian, and n transpose. Okay, there is no requirement to write a force matrix for a bar. Okay, because all those r will be 0. But again I am using the same function for the bar. Okay, so here you can see that this is the k local for beam, it will give 6 by 6 matrix. This is for bar, and for q I will use the compute force matrix, and it will give an entry q as a 0, and then we will add k local equal to k local beam plus k local bar, and this is when the element is not 1. Okay, then this will run. Okay, then after getting the k local, since we saw that all these entries, I mean this k bar matrix, sorry, not k bar matrix, that is the k, when you use ke beam and ke bar, that will be in the local coordinate axis. Okay, so to convert in the global coordinate axis, I need to use the transformation. So that's why I have used here the transformation. Similarly, to convert the force, since it is not required, because but yeah, it is required because we are using the beam. Okay, and in the beam we saw that the transverse direction will be in the vertical in the local coordinate for the beam, but it is not necessary that that will be a same global coordinate axis. So that's why we need to we need to transform that f local. Okay, so here you can see that f local, we need to also transform that matrix. So I have transformed it, and then we will use the same loop. Okay, now we have to apply all boundary conditions. So here we can see that here there is no such force, so that's why f1 2 3 will be 0. Okay, and f4 since there is no requirement, even if I use the even if I comment it, then there will be no requirement of that. But f global 5 is in the vertical direction, since it is wrong, because we are taking negative force, I mean vertical downward force, as a positive. So that's why we need to use plus 2000, or I mean it won't matter, even if you use minus 2 it won't matter. Okay, because it will be independently added, because if I talk about the bar problem, there is no such force. Okay, so it won't matter. So yeah, so there is no such moment at node 2, so that's why even if I comment it, it won't matter for us. Even this If we comment it, it won't matter. But yeah, when I talk about 1 2 3 4 5 6 7, 7, F7 is 0, and F8 is in the vertical direction, so that's why I am using minus 4000, and there is no such force and moment at 9, so that's why I can also comment it, so it won't matter here. Now we need to see which are fixed nodes, because we need to reduce the K global and F global. Okay, so what are the fixed nodes? So here one fixed nodes is 1 2 3 and 10 11 12. Okay, then it will separate from the global stiffness matrix. Okay, then it will solve the whole problem, and then we will run this code and we will see what is happening. And yeah, else is correct. Let's see. So yeah, so this is the displacement. This is the displacement of node 1, node 2, node 3 and node 4. So here you can see that there is no such displacement of node 2. Okay, since it is this code, I mean this is along the x direction, so there is no such displacement till here, and then this point when you move, then this point there will be a displacement, and again it becomes 0. Okay, so I mean it is very difficult to understand, because all these are in the global coordinate axis. When you try to convert in the local coordinate axis, then we need to again multiply the Q matrix with that nodal displacement and force displacement. All these answers, I mean all these reaction forces are in the global coordinate axis. Okay, so here also you can see that there is no such displacement at node 1 and there is no such displacement at node 4, so that's why all these entries are 0. And yeah, here also at node 2, if I see at node 2 the increase is -2, which means that that is vertically downward, and at node 3 it is -4 multiply 10 raised to the power 3. So that's why these are reaction forces. Okay, let's solve one sample problem. Yeah, since we have already solved one frame problem, then we can easily solve any kind of frame problem. Only we need to do just small modifications, and we can directly use this code to solve all those problems. Okay, so in this problem here it is taking this point, it is taking this point as a origin. Okay, this point as a origin. So for node 1 you can see that, and we need to be very careful here. Here some dimensions are in feet and some dimensions are in the pound and inches. So we already know that 1 feet equal to 12 inches. 1 feet equal to 12 inches. Okay, so node 1 we can see that its coordinate is -5 into 12 comma 0. Node 2 is -5 comma 12 into 10 comma 12, and similarly for node 3 and node 4. And what are connectivities? Node element 1 is 1 2, element 2 is 2 3, element 3 is 3 4. Okay, these are the connectivities. And AE in this problem, I mean area of all these beams are equal, which means that all these are identical, and modulus of elasticity is also identical, moment of inertia is also identical, and this is the degree of freedom for which we have to use this code. So here we can see that the degree of freedom for this node, that is 1 2 3, and here it is 4 5 6 and 7 8 9, since this one is the fixed, so that's why I have not written here, and all these entries are same, nothing we have to do it, only one thing we need to do it, to change the boundary conditions. So here we can see that here F4, we need to write F4 equal to 10 into 10 to the power 3. Okay, so that's why I have written 10e 10 to the power 3. Similarly, 1 2 3 4 5 6 7 8 9, which means that if 9, since we already know that we are taking m this direction as a positive, but this is in this direction, so that's why we need to use minus 5000. Okay, minus 5000 lb, which means that pound per inch, pound inch. Okay, lb inch. Okay, so yeah, and here also we don't have to be confused, this is proper, in this proper direction. psi means pound square inches, pound square inches. Okay, so we already converted everything, length in inches. Okay, and force in pound, and everything is correct only. So, and also what are fixed nodes? Fixed nodes are 1 2 3 and 10 11 12. Okay, so these are fixed nodes, and else will be same. Let's run this code. So yeah, this is the solution. You can see that this node, there will be no displacement here, no displacement 1 2 3. Here there will be displacement. It's obvious that the displacement along x-axis will be 2114 in this direction, and there will be also deflection. Because of this deflection, this deflection, maybe it will rotate somehow in the clockwise direction, so that's why it is coming out positive. And yeah, at node 4 all these entries are same, and these are all nodal forces. And 10,000, yeah, here we can see that this entry is because of 10,000 pound. Okay, so here also we can see that 5,000, yeah, here it is 5,000 lb inches because of the moment. Okay, so this is the problem all about the frame. Now you can solve any kind of frame problem using this code. And let's see one more thing, how this beam stiffness matrix is working. Okay, suppose, and one more thing, maybe symbolically it will not give any solution. So let's do one trick, whatever I did in the previous problem. Okay, we will make changes here, make some changes here, okay, so that it will give in the symbolic form. What I want to see how symbolically it is giving. Okay. Okay, let's assign. First I will clear it. Clear all. Let's assign some values. Sims LE EIZ. Okay, Sims. Okay, all these values I have assigned it. Let's, and also, yeah, let's run this code.